Okay, so I'll talk about maximal singular averages, but I will focus mostly on the spherical maximal functional invariance, and later on there will be discussions on how the method that we will be discussing apply to other sort of averages. Okay. Also, this is going to be part one of a longer series of lectures because there's going to be more lectures next week in that level. So I'm going to focus more on the classical methods that have been considered to study maximal singular averages, and next week I will be focusing more on modern techniques that are being developed with the years. Okay. So I'll start with, as I said, the spherical maximal function. Remind that this was discussed and then last week. Okay, sectors. We added the maximal function, and as we already saw last week, this is an important operator. Maximal functions are important operators because of their relation to differentiation theorems, right? We go into that. Sorry, and it's very low down. So it's ours. Is for all b greater than 1, that would be greater than 1. So, in contrast here, we are going to consider more singular averages than this one. Here, we are having over solid balls, okay? And the object of interest is that we recommend the averages for the just the boundary approach, okay, over the spheres. Here I'm denoting by sigma the normalized direct measure of the sphere, and by sigma the is normalized direct. Okay, and then I'm just taking the convolution of F with the measure supporting the sphere. Okay, the sphere of F. And then the supremum over the okay, so if we just why this object is important, it is the first fundamental object where we have more singular averages than the balls. But moreover, it is important for several reasons. It has connections with the wave equation. We can, we will see in a second that studying mapping properties of this object can allow us to deduce packing properties of the spheres. And also, the spherical maximal function can be used to obtain dimension-free bounds here for the Hartley maximal operator. Yeah, I'm not gonna discuss it, but this is another one, another of the application, and many more. Okay, so one can start to think about what are the possible mapping properties of this object. And in here is a very necessary condition comes in the sense that if I just say, let's say, a characteristic function of the ball or a smooth function, one portion at 0 at the origin of the radius 1, and then if we are here very far away, okay, then the decay that we are going to have now, because we are in a sphere, is only going to be 1 over x to the power minus 1, as opposed to 1 over x to the power d, that is what's happening here in the robot. Okay. So therefore, the only possible LP mapping properties it ovviamente theory that P is greater than D over the image. And this is a theorem of Stein and then again. So Stein is we can do this object. And P of the bound dimension 3 and higher, and again we get the bounds in the two-dimensional case is that we have this. Okay. So here I'm considering only dimension 2, because if we just think about what happens in dimension 1, then the sphere will just be 2 points, right? We are just going to the left and to the right by distance t. So if we were just considering an LP function that is unbounded, we could always pick up that the S of f is always equal to infinity, and therefore there are no interesting LP estimates, and then we are always here having this decision dimension. Okay, as I said, let me just say what was make sure that I'm not missing anything. Lenin has mentioned already the corollary regarding geometric properties that this implies. So let's assume that we have to, for now on always, as I said, like whatever we refer to, and let E be a subset of RD, and then for every point in E, let's consider that we have a mapping that uses a circle, okay, centered at X, okay, of arbitrary values, okay, or a sphere, right? Then this sort of theorem, besides giving us differentiation of averages along the spheres, it also gives us this type of theorems. And this is a phenomenon that doesn't only happen for spheres, it happens also when we consider averages over other manifolds. Okay. So if the set E for the centers has positive direct measure, then the union of all the spheres has also dimension. So and this is followed by considering the characteristic factor of this set of the union of all the cells. Okay? Because then here we just take now the spherical maximal function tested on the function f, then we can always make that S of f be 1 for that function, because there's also, you might take the supremum, so there's also always going to exist a radius where we are contacts. Okay. So I'm going to that type. So it is nothing but the measure of this sense. And these become down below where I said E, where I know that the S of F is one. And then if my assumption is that the direct measure of E is positive, then I also have that the measure of that union of circles is positive. And in here you can see that the exponent P, it doesn't really matter. Okay. So any LP bound here for any P finite, it's smaller than infinity, it always gives geometric measure theory result like this. Okay, we don't need to have a short range. So this in dimension 2 was proven by Maximal in a very nice paper, and this happened more or less around the same time as Burgan proved his result in 2 dimensions. Maybe it was slightly earlier, but maybe years of publication, maybe that be the same. Okay? But this can be seen as quantitative versions also of this phenomenon, just packing of circles. Okay.
Steve Pascal did it like 1980, but he was like a notorious perfectionist. So it took about 6-7 years to write a paper.
Okay, so then way earlier than way earlier than and the year of publication is, I think it's maybe even 1 year later than Burgan's, right? And then in his paper he added even in the first page, in the introduction there's even a sentence that says, "Oh, I found out that Burgan has also proven this result in dimension 2, which implies the result that he had proven was apparently the 80s." Okay. What else I want to say? Yeah. So if we look at this corollary and this statement, okay, this is one reason why it was of interest with circles is that if you consider the analog for lines, the analog for lines can have level measure 0. Okay, so these are when we take out the point x from the line. This is the Nicodim sense. Okay. So therefore circles this doesn't happen in general. Okay. So this was like a bit of sort of like okay. There's a bit of the same. Yeah, so here I'm saying that this results was for all p greater than d over d minus 1, and then one would think what happens at the endpoint, right? Is at the endpoint we have something of this type, right? So the answer is that no, in this case, we take inequality doesn't happen. So one can just define a little bit the example with some blocks, and then one can prove that the employee authority fails. In this case, yes. Okay, now I'm talking this function with a log to be precisely in LD over D minus 1. Okay, but then if I test the spherical maximal function from this function, and then I take averages where the time of the radius is equal to the modulus of x then I can, it's a computation of some base, yeah? And then I can make this be equal to infinity. Okay? We can think here, okay, let's look at dimension 2, and this becomes a log of, log, and then this equals it. Okay, so in contrast to the to the 100 maximal function, there is no weak type peaking at the endpoint. So no or one. Okay, but there are substitutes of that. We just mentioned them for completeness. One is a restricted with type inequality. The dimension was greater than 3. This was proven by again. Also, not in the same paper, but around the same times. Derivatives, if I remember now. And no better Lorentz space bound poles. So here there is and here is where this Burgans interpolation trick that nowadays is used to put restricted with type inequality appear for the first time. But however, in 2B or for B of 2, states. Okay. And these are resolved by singular opposite. Right? In 2002, I believe, something like that. 3. Okay. So for dimension 2, we don't have this angle. Okay, we have it already a functions, but here there is a set type of function in this. Okay. For real functions, this was previously known by Beltran, I think. Also this. Okay, so we can see here that I've already mentioned here for dimension 3. This was proven by Steiner there, and then for dimension 2 was proven by 10 years later. And now we have there is an endpoint result of restricted weak type that falls for dimension greater than 3, equal to greater than 3, but for dimension 2, this fails. So there seems to be here a radical phenomenon if we are in dimension 2 or dimension 3. Okay? And the question is like, why is that? Okay, so let's I should not put in subsections. That was introduction, definitions, and statement, and then now let me reflect on why the circular case seems to behave worse than the spherical maximum function case. The enemy here is tangency of cellulose. Energy. Let's see that last time in another necessary example that wasn't shown up yet. Okay, we shown up here the tutorial example and the same example was just with the logs. Let's look at another example that it wouldn't be necessary to really generate new necessary conditions here, but is illustrative of why there is this dichotomy between dimension 2 and 3. Okay, and the example that I'm taking is under a delta neighborhood of the unit circle. Okay. Let's, for instance, we'll take the following. And I'm gonna look at what happens, let's say, here. Okay. Well, for instance, I'm gonna just take a point here, x, to be my center. This is the function. And I'm gonna take a point next to here. So x I'm going to assume that the third d minus 1 coordinate is 0, yes, 0, and then for instance, I'm going to do the last coordinate is between 1, for example, it doesn't go down to even smaller. And now let me be 1 plus xt. Okay. So what I'm doing is with this column, I'm making this radius and making that sphere. Okay, so that are point.
So x prime is this first d minus 1 coordinates, right?
Yeah.
You are these two. So
No, well, I can run this example for any that I really did. Okay. Because then we'll see why this example wasn't there all of that. Okay. Okay, what we will show is that there is a lower bound governed by the power d minus 1 over 2 for delta. Okay, and because of this, the example, this f is symmetric, and we are taking averages over a sphere. As soon as I have it for this point, I also have it for all the other points, right? Okay, so this example is information invariant. Okay, so then equation this bound appears over here. This bound goes through. The root, okay. And so so an LP bound for the spherical maximal function here, we would imply the LP norm of this is just the thickness delta is a measure we will over 1 over t. However, we have this happens in a domain of one size, okay, the measure. So the model doesn't really affect, and so we already have this value. Okay. So let me go to 0. We get a that is greater or equal to over the image. Okay, so let us, if we compare with the other constraint that we have. Okay, we can see that these two, they match when the dimension is actually 2. Okay, so the example that we just gave here, it shows up for dimension 2, but for dimensions 3 and higher, this is a much restrictive threshold. So here, this tangency of 2 circles that is appearing here is not playing any role in dimensions 3 and higher. Okay? But in dimension 2, it does. It's an enemy that we have to attack. Okay, and this enemy that we have to tackle is the reason why the methods that were developed in higher dimensions, they did not help we can mention too, this is very bad, okay? And Jonathan, if you see this objective, he's gonna focus on how to overcome that obstacle. I also will discuss how to overcome the obstacle with Fourier analytic techniques in like decoupling and square function and so on next week, okay? But I will not focus on the circular case, but this example is illustrative of why this is part of theorem. Okay. Okay.
Could I make a comment?
Yeah, of course.
There's another way of seeing the difference between d equals 2 and d being equal to 3. So if you actually look at on radial functions, then the averages become radial. So you have a very explicit expression for the kernel. I mean, it's a little bit complicated, but it's explicit, and you see the difference when d is equal to 2, it's singular.
Because of the weight, right?
Yes, exactly. And d equals 2 is singular, and d being equal to 3, that singularity goes away.
Yeah. And later on, when we are going to explore Fourier methods, you will see also that the decay of the spherical measure, it gets better with the dimension, and dimension 2 is smaller, so that's another manifestation of the same properties. Like that. Okay. And I wanted to run this example, but I think it's just a computation, and if I do it, I'm gonna spend too much time, and maybe I'll just keep it if I have time later. I'll use it. But it's a computation, it's not very hard. It's overall. Okay. Okay. This is also many times called the NAP example. Although the NAP example typically, instead of taking this delta annulus, people just look at this rectangular box. But it's the same example. Okay. What's the difference is that this NAP example comes out to be more helpful when one studies a necessary condition that implies a P2 equivalence, because then the bomb here is no longer rotation invariant. Okay, as soon as I take it here, if I take any point here, I can always rotate it to this situation. But when I have a fixed box here, the example no longer becomes rotation invariant. So then the only region in which I have this example is like also like a box here, okay, with matching the sizes of these, okay, and then this is no longer a set of measure of 1 on the left, and therefore it appears here. The exponent q becomes relevant, okay, but it's the same example. And yeah, let's keep the computation. Okay, if anyone wants to discuss it later, we can discuss. Okay. Okay. What? And let me. And what I'll tell you today is to give the proof of dimensions 3 and higher. Okay, that's the model for today's lecture. And so for that, I'll run a bunch of standard techniques in Fourier analysis. Eta is going to be always this kind of function. Okay, is 1 near the origin, and then has some support in the ball of radius 2, and then and this is about the rectangles, and I'm gonna put here J to be one organic frequency J, so that I have a position of unity. Okay. And then the problema that I'm gonna have, or what I define. So that affects the frequency localization of the Fourier transform of the spherical measure at frequency to the day. We beta replace beta z replaced by beta okay. Okay, first of all, here know that this is different than if I consider a frequency that of the function f, okay? So here what I'm doing is I am taking the Fourier transform of the spherical measure, okay? Just forget that it's dilated, okay? And I'm breaking this up into a decomposition, okay? Into the part near the origin, and then the part that goes to the J. And then I make the dilation. Okay? This is different than if I just take the, this is different than doing maybe a put in red. Different than doing that, which is what we be coming what is written here. Okay, the parameter values. Okay, so the first lemma, which is the standard. Is that the one at frequency 0? Okay, that's controlled by the Buchanan maximal function, and which is just 0 sequential this function of frequency company supported, so then of course such as much as I want. So then here the x is, I don't know, greater than 10, for instance, then I have that I can control this by streamline gen, and then the opposite happens. Then this corresponds to 1. So this is bounded by this by 1/1 plus s to the n. Okay. For any capital N absolute 1. So when I take t dilations and then I convolve, this is therefore controlled by the analytical maximal function, the function we already have. Okay. So in particular, that term is controlled by that. Then we have LP logs, so we can forget about the J for the term. Okay. So then the goal, and at least as you can see, I'm not using really anything about the sphere. It's a very general phenomenon, right? I could just replace sphere by water. So then we will focus is on fixing AJ and then obtaining an LP bound with a factor of 2 to the minus J epsilon, and we can sum over the frequencies. Okay, we're going to do next one. Okay. Goal. Second reduction. Um, okay. I'm gonna define this as J capital I to be the one where the supremum is only happening in time to 1 and 2. Okay. And the reduction that I have is the following is that when at least the P is greater or equal than 2, okay, I can just focus on this guy. So this never tells me that if I have the inequality that I want when the time is between 1 and 2, then I can put the time scales together and deduce a global bound. Okay. And here I'm requiring that P is greater or equal than 2. Okay. So the proof of that is essentially a weaker version of the Kelvin theory. We don't need to do the theory, but it's sort of an easier variant. Okay. So let me just display the supremum. And the very supremum into radiative scales, and then I just take the time between 2 to the k and 2 to the k plus 1. Yeah. And then here the key realization is to identify the fact that 2 to the k entity here, then I can do a rescaling, okay, of this quantity. Then I can put this back to an operator where the time is between 1 and 2, but then these 2 to the k factor that was there, then it goes to the function and it goes to the evaluation of the argument of the output. Where x is k x. Okay, so then my hypothesis the inequality that I have here rescale to this factor, okay? Because it's an LPLP bound, and the rescalings they cancel out, okay? So then the hypothesis implies this. And now let us consider LP bounds for now the global operator. So Then here is this supremum in K. Then I can replace it by a little LP sum. Okay. 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 Well, this factor is the same. It's totally the same as this quadrant, you know? And then I could apply that one, but with the following observation that now that I have fixed the K, now that the K is fixed, and I look at what happens at Fourier side of this one, this on Fourier side is one. Okay. Where the time is about one, and this Bj is like putting here a K minus J. Right? So this is supported, each of these guys is supported where the side is about 2 to the J minus. Okay. So then I can put a reproduction cutoff here, that is one on the support of this function, and then vanishes in the double of that support. So I could put an extra here until J minus K. Okay, but I keep it, and then I can keep it here on the right-hand side of the quality. And in order to do this trick, of course, it's been very important to fix the K, right? To isolate the K from the operator. So I'll apply the quality, and then I get okay. And now I think I have this literal sum. So if I were for P equal to 2, okay, these guys on Fourier side, they have essentially going to overlap, right? They are disjoint, but maybe overlapping a little bit, but then it's going to be to norm of the function. And then if I'm at infinity, this sum becomes a supremum. Okay, and these are one normalized function. Okay, so both estimates one has them at P equal to 1 and P equal to infinity, and therefore you have them for the visit. Yes, I use this. So this is a weaker version of little Berry theory. We wanted to could also turn this into a square function, okay, inside, and then apply little Berry is thinking for a square function, but it's not necessary. Okay, so then we have those reductions, okay. And so, but this is only it only happens at L2, right? So then the idea is going to be to at L2 use this reduction, okay, that we can only focus on the local operator, okay, and prove a very good estimate using the two methods, okay, for the SI until, and then at L1 a bad estimate for the global object, okay, and then because this implies something for this one, then we interpolate these two estimates, and hopefully they are going to meet P equals 0 dimension. Okay. Okay. This is not, I think there is a problem. So let's start with the L2. And I also want to emphasize that the same way as I said earlier, that the SJF is different from the S applied to the little value frequency of the F at the scale J, that they are not the same. Now, when I have localized at 4 times equal to 1, okay, SIJ and SIJF, now they are morally the same. Okay. So now when the time is between 1 and 2, the dilations they don't matter. And then more or less it is equivalent to consider one operator or the other. Okay. But in the sense that the same method applies to both of them. And for instance, for the singular maximal function where the p is greater than 2, one can indistinguishably decide to frequency localize the measure or frequency localize the function. It doesn't make any difference. But here, it has been important to localize the measure because at L1 is not forgiven. Okay? Because we need to consider the global. Okay. Okay, and now it becomes a standard lemma that has been is very easy. Okay. But allows us to replace the supremum by a time intervention. Okay. So this lemma is the proof. It has the fundamental theorem of calculus. Okay. We just try. My fundamental theorem of calculus, I can control I can control this by the n value at 1, which is the left hand point, and then I take the derivative of my function. Okay. And now I'll just apply Felder with exponent p over p minus 1, with therefore it gives, which is the p prime, and therefore we do the 1 over minus 1 over p. Okay, and then we can be here. Okay, and then I need the things. I control this p. Oh, sorry, I should have put s where usually okay, and I can control this t by 2, and that's it. Okay, so and now plus something. Okay, so let's apply this to xi fj, okay, because it's the quantity that we are interested in bounding for p for p equal to, okay. And by doing that, then we need to study what is the derivative with respect to time of these averages, right? So understand what is that and here,
Sorry, what's SIMJ? Is it the same as SIJF?
Yeah. But when we are localized, it's essentially one of the other. So now we can derivatives with respect to time of these averages, okay? And for instance, I can use the expression in Fourier side, but these guys are one of the again, I will image the transform of the transform. So I haven't yet talked about what is the Fourier transform of a spherical measure, but okay, this is the structure. So then we have here that the time appears in these two places, right? So one possibility is that it is here, and then the second possibility is that it's going to hit here. Okay, if it hits in the first one, then the derivative with respect to time of that it will be the gradient of psi and the derivative of sine hat. Okay, and then when we hit here, again it's going to be this one is like that. Okay. So this one is going to be increment of j psi with the gradient of the beta evaluation. Okay, so we are going to have the sum of these two terms depending on where the derivative lands. Okay, so this guy is fine, okay, because the psi is localized escape to the j. So then this is in terms of size, this is all of 1. And then here I have nothing but another cutoff, okay, localized at the same place. And then I have continue to have the spherical measure and so on. So this is essentially like the average. It's not, but it's essentially like the original object that we started with. Okay. And then, but when the derivative hits the first function, the spherical measure, then we are pulling out here upside an order of magnitude of 1 of the frequency. Because the spherical measure of psi hat, okay, this is now what is coming down is the x, right? But the x is in the unit sphere, so it is not really affecting to the size. Okay, but here we have a power of 1 of the size, the frequency which is coming out. Okay, so we can be thinking that this guy, the derivative with respect to this guy, is essentially going to be like because this is localized 2 times j the original spherical average. That's the behavior in terms of magnitude. Okay, so because that derivative comes with the power 1 over p, okay, then the whole thing essentially what I can reduce it to is the following. Assume that now it's a lot of years after good. Assuming that we have this inequality, okay, for some epsilon p, okay, for some p and for some epsilon p, okay, greater than 0, and that we have managed to do it with an extra here 1 over p, okay, but when there is no superior, when there is integration here over time after applying this little lemma, okay, so then this implies that the S A J F by applying that we multiply the same, but with the factor to the regime. Okay. Right. Okay, so this has allowed us to reduce this estimate for p is greater than 2 to now an estimate in which we have LP of RD 1, 2, and in here I have sigma B J. Okay. If this happens with a minus J over P, then this happens. Okay, that's the new level. So, in order to effectively use the methods, what we do is to study the Fourier transform of the spherical measure. Because as I said, we were using 1 and 2, and now here we're going to have another estimate. So I can even fix the time between 1 and 2 and study I can have a branch ahead, right? And twice, and then just focus on the everything of the multiplier that we have, right? So then it's fundamental to understand what is the behavior of the spherical measure, okay? And where here we have time between 1 and 2, so there we are localized at the scale side. Okay. And, so, well, very well, there are, I'm running out of time. So, this is one instance of an oscillatory integral, right? And then here one needs to understand something about oscillatory integrals, right? Which are more general objects of the following type. They are also the following type, and then one works depending on what is the phase function that we have here, and the relative cutoffs that we have here, what is the behavior of that when the rest of lambda. Okay, this we can see, for instance, well, there are many ways to do that. One can change of variables and go into Bessel functions, and then for Bessel functions use the one-dimensional theory for oscillatory intervals. Okay, one could also just use the theory of oscillatory intervals in the dimensions if one wanted, right? But let's, for instance, just look at what happens in the situation of dimension 2, okay? So that we have a one-dimensional one, okay? And we don't have to do a spherical series of variables. Then we can address this by cos theta sine theta, then times sine, then d theta, right? And the theory of oscillatory intervals will tell us that this behavior is determined by the stationary points of the phase function. Okay, I would love to have more time to discuss this, but I'm being slow on what I wanted. So well, I think this is quite well known. And here we can see that if this is my phase function, okay. Here I can see that this is normalized. And this plays a role in the parameter pattern, okay. I could look at when I differentiate, I get a minus sign, I get a cosine. So then there is a critical point, but actually two, right? But then when I differentiate again, I go back to the original phase function. Okay? So then I cannot have that it's a double zero. Okay? And therefore I can apply my lemma with two derivatives, and then I get the rate of decay is minus a half. And I can do that in 5 dimensions, and there are d minus 1 dimensions. So I get that the decay rate is because I always need, I'm okay with using the dimensions. One can be more precise, there are asymptotics for that, okay? And with the asymptotics, one can use that. This actually behaves like this. Well, as I said, there are 2 points here because there are 2 critical points. There is the north pole and the south pole. Okay. So I'm summing over these 2 options, and then there are error terms. Okay. But in these lectures, in this week, this is not going to play a role. Okay, this oscillation. But for many other aspects of spherical maximal function, and for the circular case, actually, it does play a role. Okay. But next week we will exploit this in a more we will exploit this next week, but here the decay is going to be enough for this week. Okay? So in any way that tells us that this is bounded by e to the minus j e minus 1 over 2. And therefore that gives us a very nice to estimate. This is for all times between 1 and 2. So of course also extends by trivial iteration in time because of course the time is bounded. It also extends for time into 1. Okay. And so this for when I read it in terms of the maximal function, what gives me is when I put together everything that I said, is that now the power in L2 of the decay of the frequency is d minus 2 over 2, because I'm losing an extra 1 over 2 from the argument of replacing the sub by the time integration. Okay, so you can see for dimension 2, this is nothing. Okay, this is just a bound in L2 but has no decay. Okay, but we are in L2, which was the endpoint, so we cannot expect decay. Okay? So it's but then it means that these L2 methods are not going to be enough. So this is the very good L2 bound that I mentioned here. Okay, because remember that for dimension 3 and higher, we need to meet this d over d minus 1. And then there's a kernel argument, okay, here for the 1, which I do tomorrow, and with that we conclude the bounds in dimension 3 and higher. Okay. Any questions?
Yes, thank you, David. It's time for discussion. Any questions or comments?
So the original was time used complex integration, right?
Well, it's because he considers a more general family of spherical maximal functions as well, right? And you can consider this generalized with a second parameter, there's a parameter embedded into the operator, and then I think we use complex interpolation to deal with those more general.
But it also gives this, right?
It also gives this, but you don't need the complex interpolation for it. No?
Can you explain this proof with fundamental calculus?
Yeah.
This first step.
This first step, yeah. So, okay. If you one, you can, okay, for P equal 1, I guess that you don't want to consider integer modulus, right? Because then you might have some differentiability issues, but then you just put the absolute value later inside, okay? And you don't care. But for P greater than 1, the composition of the a differentiable function and the modulus to the power P, that's all differentiable, there's no problem at 0, okay? And then what I'm writing is a function. Let's say that this is a function g, right? And I'm writing g at 1 plus the integral between 1 up from 1 to t of g prime of s ds. Yes. Okay, but g prime of s in this case is p. Here it is p the function to the p minus 1 and then the derivative of the inside. Okay, I am applying the chain rule here, and then I get f prime of s, and I'm putting now all the absolute values inside if I want, and I'm controlling the t by the 2, okay? And now I'm going to apply Helder. Okay,
like this step from this after we get this inequality, applying Helder is easy. Maybe I don't see how we are losing this power to the p of f1 because after Helder these integrals will change to this from the power, yes, but we have this f1 to the power of p. What is how we are losing this p?
Well, the exponent is 1 over p prime actually. Okay, I mean,
do you mean this? Sorry?
No. First, this is the theorem. Like after this inequality, in the proof you have f from the 1 to the p.
F from the 1 to the p.
F1 to the p. Like the first.
Oh. So,
Well,
here.
Yes. Okay.
Yeah, sorry, that was a typo. Yeah, so this is a fixed time. This is a fixed time object, so it's satisfied. It has no loss. Okay, and this then here it carries a loss because this has no loss, and this one has a loss, and then it carries some loss. Okay. Sorry, I had missed something.
May I ask one question?
Yeah.
It's a bit philosophical question. So, in this theory, is there any discrepancy between even and odd dimensions?
No.
Okay.
For the maximal laws, the only discrepancy is between 2 and.
I mean, results, applications, and so on. No discrepancy.
Yeah. Okay. Well, for wave equations, then for this type of Kirchhoff formulas and things like that, then things the vary a little bit between the even and odd dimensions. But for bulks for the maximal averages, no.
Any more questions? Well, if not, then thank you, David, and we have a break.